Yes, hello and welcome to my talk about the general mathematical proof of Occam's razor. And then I'm also going to show an upgrade to the methodology of the physicists. Going to start with history, Aristotle. The reason he's at the center here of the image is because he was a very central figure that influenced all kinds of fields, geography, invented logic, and so on and so forth. And yeah, he also invented Occam's razor long before Occam. And this is whom the razor is named after. It's actually named after the town where he's from. It's Occam's razor below in blue. And the arrow there, it represents the scientific revolution. If you think of scientific revolution and people from around here also, then of course, who comes to mind is Newton. In a time when people believed in all kinds of superstitious stuff. So he invented he had all kinds of inventions. Mirror telescope is my favorite. Yeah, and what's the secret behind his success? You can see it in his Principia. Rule number 1 is Occam's razor. And if I talk about Newton, I also have to talk about Einstein. People are going to ask me anyways, like, did Einstein use Occam's razor? And they will say no, but general relativity is complicated and stuff like that. So it's not, it violates Occam's razor and all kinds of stuff like that. But anyways, I'll just give you an interesting story. So there was a time when when Einstein started ignoring Occam's razor. And it cost him 3 years. He wasted 3 years of his life working on publishing wrong versions of general relativity and having stagnation, all kinds of delay. There's still actually something blocking my view right now here in the screen, but okay. Then he started to become desperate because mathematicians and other people were catching up to him, so he would have lost priority. So then he accepted Occam's razor, and very shortly thereafter, he already figured out the right theory and he published it here. Actually, that's a realistic timeline. You can see the green arrow there. It's really tiny. So that's how fast he figured this stuff out. But really, he figured it out already 3 years earlier. He just he wasted a lot of time just because of not using Occam's razor. So that's a really extreme example of how not using Occam's razor makes you fail. And I didn't make this up. This is the reference that describes this story. Okay, and then after that, he had many quotes praising Occam's razor over and over. And yeah, yeah. And this final one says also that he believes that Occam's razor will be the key, yeah, to figuring out, to advancing, to understanding everything in physics, basically. And that's also the reference I have here. I didn't just AI generate them; they are actually from a book. Okay, yeah, you never know. Yeah, so this is Occam's razor, but there's a problem, which is that it is quite vague. So this is not clear, right? What are you talking? Which entities are you talking about? And then why should this even be true? How do you even quantify this? And even this is not clear because necessity is a matter of degree. Something could be more necessary or less necessary. So everything is unclear, basically. So to fix this, we have to mathematicize it. Basically, the difference between philosophy and science. So this philosophy of science, but the difference between them is just basically science uses more math, so it's less vague. So then from philosophy of science, we get to science of science, which is meta science, and that's basically a meta science talk. It's less vague, yeah. And there were attempts of proving Occam's razor in the past that failed. They were trying to do it without algorithmic information theory. Multiple attempts. So that's the main reference about all these failed attempts. And then pack learning also had a similar problem also with failed proofs. Basically, the problem is just lacking generality, and Kolmogorov complexity gives you the generality such that, well, people won't find some special case where it fails or so. Okay. Solomonov, so he mathematicized Occam's razor, but he actually didn't prove or didn't explain why it's true. I have to just check how I am with the time. I don't know. I have no idea.
I give you 5 minutes. Sit down 20 minutes.
Okay. Yeah, so various improvements were added to this argument, to Occam's razor, to the mathematization of Occam's razor, and to the proof of it and all that. But it has never become widely accepted, and people, for example, physicists don't understand it at all, actually. And you can see this from there's one scholar that wrote a lot about, he was criticizing Occam's razor, algorithmic information theory, all that stuff for like 300 pages or so. That's how you see that it didn't, it wasn't accepted widely or anything. And that's the end of my history section. And so this is my goal. I'm just trying to fix all that stuff. Yeah. Oh, yeah. Good. Thank you. So model complexity, it's important to define what that is. That's the guy, his name was Algorithm. That's where it comes from. Science should be objective, reproducible, falsifiable, all that. So it should be, scientific models should be clear, basically. So to circumvent falsification and all that. And that means they should be clear instructions. And clear instructions, they are just algorithms. That's pretty much what algorithm means. And then, we all know this Church-Turing thesis, and also that's all this stuff about universality of Turing machines. So we can have we can just make a one-to-one correspondence between scientific models and computer programs, basically. If we assume that we just include all possible programs, that every program is a model, basically. That's actually also Epicurus' principle. I should have mentioned that maybe. Or maybe it's not, I don't know. Scientific models. So then one-to-one correspondence here, yeah. Oh, yeah. I noticed in the algorithmic information theory literature that oftentimes people just they just use the words model and theory interchangeably, but that's not a good idea. The theory is actually more than a model. It can consist of multiple models, and it can contain theorems about models and all that stuff. So if you go into another field of science, people will be confused. For example, if you would say my theory is simple, they will disagree with you when you actually meant that your model was simple, because they don't mean the same thing. Just saying. Okay. So how do we choose the reference form? That was an old problem already. Solomonov raised that, or he was talking about this, I think, a long time ago. Yeah, size of a program, but the problem is in which language. And there are also many names referring to the same idea. So Komorov called it description language. It's also called the choice of the reference machine, reference language, reference computer, description method, all these different terms and more probably. So I had to choose one of them, and so I just made up another one. Yeah, but that was the only one that made sense actually in the end. And the claim is that the reference formalism is supposed to be simple, but there are problems with that claim. So there are two objections. Both of them involve some kind of circularity. So firstly, how could we possibly select the least complex reference formalism if the definition of complexity already depends on the choice of a reference formalism? So that's like circular definition. And the second one is, if we postulate that the reference formalism ought to be as simple as possible, did we not just invoke Occam's razor, and therefore any proof of Occam's razor derived therefrom would consist in a fallacy of circular reasoning? So circular reasoning. So and it's also important to distinguish these two, because if you confuse the two, if you conflate the two, you become even more confused. So I just explicitly distinguish them. Okay. There were some attempts to solve that. There was this complicated attempt by Markus Müller, where he tries to solve this by having many machines and seeing how they how well they emulate each other and all that stuff. But he actually then figured out that his own approach is not going to work. But it's still a great paper. I mean, negative results are also valuable. So how do we actually solve this? This solution is not that, you don't need higher mathematics for that. Untyped lambda calculus is it's so simple. It's like similar to if you show somebody maybe Euler's identity for the first time or so, where they are just astonished, right, of how simple something can be. Because we are used to programming languages or systems that have universality. We are used to them being much more complicated. Yeah, that's why. And for the second objection, it's not circular reasoning, because there's another reason why it should be simple, which is not Occam's razor. And the reason is that complicated reference models could be like abused to declare some complex models to be simple. Because you could have like a complex subroutine packaged into a simple looking function or something like that. So that's why this has to be simple. Okay, these are the two resolutions to these, so that's out of the way. Then lambda calculus, there are many other reasons also to use it as a reference formalism. Besides its simplicity, it's also widely known still, and also it's built into various programming languages, and its original purpose was mathematical logic. So that's also maybe useful if you want to do, if you want to figure out like how complicated is a mathematical model in physics, for example, right? And yeah, that's why this should be the reference formalism for everyone. And there's a problem, which is that it's not expressed in terms of lambda calculus is not just a binary code, but all of algorithmic information theory is expressed in terms of binary codes. But John Trump already figured all this stuff out. Yeah, that's his reference down here. Yeah. And this is just for fun, some of John Trump's stuff here. So he invented these diagrams also, and here's some animations of it. And they were provided to me by this YouTuber. Thank you for that. That's not me. This YouTuber is not me, and this is also not John Trump. We are three different people. Okay, I'm just saying. So now we come to the proof of Occam's razor. Initial assumptions. So of course, we cannot use Occam's razor as an initial assumption, or as it would be circular. Somebody once proposed, it's like stated, the great programmer as a, the screen is off here. Oh, now it turned on again. Great programmer as an initial assumption, but we don't need that. Computability of our universe, somebody proposed that as an initial assumption when proving Occam's razor, but we also don't need that. So it's also the claim is a bit too strong, metaphysical and all that. So let's just cross it out. I just make the initial assumptions, some nice assumptions about science, Church-Turing thesis, Epicurus principle, basically. And of course, the simplicity of the lambda calculus, and then some assumptions about just keeping things reasonable, fair, neutral, yeah, impartial, and so forth, yeah. So these are the 5 initial assumptions. And then I think anybody can agree with all of them, or is there any objection, or no? Okay, good. Yeah, everybody already knows Kolmogorov complexity here, so I'm just going to skip. And here's the structure of the argument. So I here took a frequentist approach, but you can also translate everything into a Bayesian framework. It's all fine. So in my analogy, I just use some politics analogy. I don't care about politics, but most people know a lot about politics, so that's why I'm doing this. It's easier to understand like this. Okay, so the models are the voters, and the past observations, that's like the people that are allowed to vote. So they have to, basically, that means the models have to agree with the past observations, and the predictions is what the models are voting for. And this arrow, maybe you can call that universal induction. That's how you get from past observations to predictions about future observations, okay? And now the argument goes that we just maximize the charitability toward high model complexity. So we just let it go toward infinity. And then despite that, all of that high complexity, so there are only the most complex models voting. And the outcome of this election is actually, screen is off again. Well, the outcome is it agrees with the simplest models, and that's what proves Occam's razor pretty much. And also, yeah, there are many people that contributed to this, and I don't have time to list all of them. So I will just continue. So how did I construct this proof? This rule is Shannon's chain rule for entropy. It's called chain rule because of what you see here on the side. And the proof is very short, and it's very intuitive, so people can understand that. But that's of course not good enough for our proof, because we don't need entropy, we need Kolmogorov complexity. So here's a chain rule for Kolmogorov complexity, which I'm using. And also, this is still very intuitive. And it already has all these complications of like Leibniz's coding theorem packaged into it, so we don't need to deal with that. So then I just use this to build up the proof. It's yeah, that's also another rule. So this is the definition I use, and I just build up on that, and then I get to this exponential relation, and then yeah, okay, I should also add here independent variables. That makes it a bit more general. That's also part of science, to have independent variables that you put into the model, right? That's basically the z in this the letter z in this theorem. So then there's another theorem which is about probability ratios. But here's a problem, which is that there are these deviations, and these deviations, they could be like possible. Trump estimated them to be thousands of bits. That's kind of a lot. It's relative, right? But if the difference is larger than that, then it should be no problem. But if the difference is smaller than that, apparently there's a problem. However, I then, after having wasted months on trying to make these constants smaller, I then figured out, actually, you can just ignore these constants because it will cancel out, but that looks ridiculous. So, I mean, it does not seem correct. So I just made I came up with this long objection, which is very explicit. And then there was this paradox. So on the one hand, I had this, which said they should cancel out. And on the other hand, this long objection to it, which says, no, you cannot ignore these deviations. And then I found out, okay, this is actually based on a false dichotomy fallacy, this objection. So the paradox is resolved, and you can actually just ignore them. So it also is valid for small differences. You can still use the same formula. Okay. So what's the secret? So here we have the exponentials, and that's a secret behind Occam's razor, the success of Occam's razor. So here's an example. For example, if the difference in complexity is only 30 bits, it shifts the ratio, like you get 1 billion to 1. And obviously this is tiny and this is huge. So that makes it highly effective. That's why you can just basically discard some models that are a bit more complex, because the probability shrinks to close to zero quite quickly. Yeah. And now I'm gonna get into physics. Yeah, an objection, because our surroundings look kind of complicated. So does it contradict Occam's razor? Because like I just said, Occam's razor is a pretty strong statement. No, it doesn't, because actually our universe could be really simple, like Tegmark also says. But there's another reason, which is that Occam's razor doesn't even dictate that the universe has to be simple. It actually, or the math also, it just says that if you don't use Occam's razor, you're going to fail, basically. Okay, and what about average many worlds interpretation? Because that looks even way more complicated. Some people think it contradicts Occam's razor, but actually, yeah, that's irrelevant. That's relevant, and it survives. So it's okay. Many worlds interpretation is okay with Occam's razor. I cannot read it because there's stuff on the screen here. Well, oh, okay, yeah. I have two screens here already. Okay. Hey, why is it not? Oh, okay. Oh, it works. Okay. Yeah, so there's some other problems, but actually these other problems, coincidentally, you can also resolve them using algorithmic information theory. But yeah, this is not the topic here. Here, the next topic, the important topic, is the stagnation of fundamental theoretical physics research. So here are some quotes by Hossenfelder. And yeah, so you can see that it's going really badly. Some people don't admit it. And it was already like that since the 1970s. Yeah, it's kind of a disaster. And she's not the only person saying that. So these are some big names also saying that. And he's not, Unziker is not such a big name, but he wrote many books about it. So I'm mentioning him. And this is Sabine Hossenfelder's book. Okay, these are the four that I cite. So this problem, I thought about this problem, and I think it's about research allocation, actually. So resources at multiple levels here. So there are too many papers, for example, here at the lowest level. So how do you correctly figure out how to allocate these resources? I have to skip because the time is kind of I'm kind of running out of time here. Actually, optimal order problem solver already said a lot about that. And here's a quick summary, but I don't have time to get into it. Sorry. So this optimal order problem solver, so it starts from small problems, it gets to more and more difficult problems. But of course, that's not all. I mean, reality looks more like this. And that's also how physicists try to tackle it. They start with these quite difficult problems, but that's also not a good thing to do. You actually have to start from the easiest problems at the bottom, and then that gives you much more attack surface. But usually they just do that. Okay, so you have to do that, and one needs to standardize all of these problems to make it scalable, to make it effective, because then that will allow you to have rankings of all the solutions according to model complexity. So each node here would have to contain a ranking of all the solutions that people figured out. That would actually make it scalable, and this would actually fix the stagnation. Here's a direct comparison between experimental and theoretical physics. And you can see basically on the experimental side, they calculate statistical significances, but on the theoretical side, they don't have theoretical significances that they calculate. And that's basically the root cause of the stagnation. So the theoretical significance, they should actually calculate model complexities and report them in the papers. Then they would actually, it would be very easy it would be much faster. You could much faster figure out which papers are good, worth reading, worth studying, worth reusing, and so forth. That would greatly increase the efficiency. Yeah. So these are some old methods that they were using. 3 old methods. Here I just explain why they are not good. And yeah, so they don't really work. So for example, I'm just going to go to the first one, counting postulates. So a postulate could contain a huge amount of information or little information. It's not a postulate is not unit of information, right? So that doesn't work. Okay. So how do you do it then correctly? So here's, so if you have a model, you should just, as a physicist, you should just put it into some, actually, all of this should be automated. I should say somebody should automate all this. You should just put it into some computer algebra system, and then it should be using the Lean library to look up all of the definitions and axioms and all that stuff that is behind that formula. And then, yeah, here's the Chaitin's definition of the complexity of a formal axiomatic system. So it would use that, and then it should all be translated. So because it's in a formal language like Lean, it should all be translated into Trump's binary lambda calculus automatically. And then, yeah, you get binary code, and that's how you get the model complexity. So the physicist could just put this mathematical model into some computer, and then it would just spit out some number that is the model complexity, and he has to report that. So that's Occam's razor again, and then remember everything about it was unclear, and to the physicists it still looks like this. They don't understand it at all, but we understand all of this basically. And we also know how to scale all this stuff up now, scale it up to, fix the stagnation, and yeah, to make all of this, actually all of these have to be standardized, all these problems, that's a lot of work. To make all of this happen, and also the software to make all this happen. A lot of people have to collaborate. Some people, I don't know how many, but yeah. Then you can, regularization is mentioned there. That's a term from machine learning, which just means you penalize high model complexity. So here, meta-mathematical regularization of fundamental theoretical physics will be the result of that then. And then, yeah, that fixes the problem of the stagnation. And bibliography. This is the main paper. This is my own paper. And then this cites many people like Hutter, Chaitin, Schmidhuber. And yeah, you can find the other 100+ references in my paper under this link. And you can just send me emails under this email. Yeah, that's the end. Thank you.